Hi, everyone. Thanks a lot for coming so late in the day. Today, we're going to talk about incremental iceberg table replication at scale. So my name is Sihan. Currently, I'm a software engineer at Databricks. I work on the Spark team on the Iceberg Delta Spark integration. Prior to this, I was actually at Apple for 4 years, where I worked on Apache Iceberg, and I'm an Iceberg PMC member. This is my friend Hongyue.
Hey everyone, this is Hongyue. I used to work at Apple as well and work with Sihan on the Apache Iceberg. Did some contributions, and really glad today I had the opportunity to share this with the rest of the folks.
Yeah, so we'll present some work that we did at Apple called Incremental Iceberg Table Replication at Scale. Yeah, please complete your surveys after the talk. So first question, how many of you use Apache Iceberg? Oh, wow, cool. Oh, wow, okay. So I can go kind of fast through this deck then. Yeah, I'm a big fan of Apache Iceberg. So Iceberg, as you all know, is an open table format spec designed for huge analytic data sets. Basically, it's a spec how to lay out metadata files and data files in a data lake and make it act like a data warehouse, right? And the advantage of it is it's all community-driven. It's owned by Apache Software Foundation, and it's built on technologies that themselves are owned by Apache Software Foundation, like Parquet, Avro, et cetera. And with Iceberg, you get all these really cool features for a data warehouse, like highly performant ACID transactions, row-level updates, deletes, safe schema, partition evolution, rollback, et cetera, et cetera. Iceberg is a spec first, so has a lot of implementations under the Apache Iceberg umbrella. Like the PMC, we govern the projects that implement it in Java, Python, Rust, Go, C++. And there's a ton, I think, growing number of OSS projects and proprietary projects, proprietary vendors that read and write Iceberg. So that's a really huge growing ecosystem. And I think one of the strengths was there was such a demand for an analytic data warehouse storage on kind of open formats. So with that introduction, so that's all the good stuff about Iceberg. One of the weird stuff about Iceberg for me was when I first started is something very simple is actually very hard. So as of Iceberg 1.7 until 1.8, there was actually no good way to copy an Iceberg table. And that's kind of one of the artifacts of the spec in the initial design. So Iceberg table spec, I think one of the strengths was it always prioritized being specific. So you don't ever want ambiguity in the spec. That's how you have tons of engines able to read and write the same format. And as part of that, it chose the absolute paths for all the file references of Iceberg. So metadata files point to other files, and all those references are absolute paths. And that actually makes it super hard to copy the table from one place to another, because once you copy it, all those references are broken. So things like just migrating a table from data center A to B, or even copying a table from this directory to that, or more I guess for Apple, backup disaster recovery, that became really hard, surprisingly. And to show you the extent of the problem we're dealing with, this is the Iceberg spec. So it's a spec of metadata files and data files, right? So the problem starts at the very top. Even the top pointer, the catalog pointer, it points to the table version file, the metadata file, and that itself is an absolute path. Then you have that pointing to the child, which are the manifest lists, for the snapshots. Those are absolute paths. They point to the manifests, which are absolute paths. They point to data files, which are absolute paths. And keep in mind, this is actually kind of an older diagram of Iceberg. I don't think it's been updated. There's things in V2 and V3, like position delete files, point to data files, which are absolute path references. And then in V3, there's delete vectors, DVs, that also point to, again, absolute paths to data files. So copying an Iceberg table of this to another location breaks all those references. So that's something pretty frustrating for users. And so how do people kind of work around this problem? There were 3 main things people tried, or at least what we tried. The first is kind of you can always use your favorite query engine, Spark, Trino. You do create table as select, or alternative create table and then insert into select. Basically, you just select all the rows and then write it back to the second location. This works okay, but I think the drawback is obviously this is quite expensive. You have to kind of read all the rows, process them, deserialize them, potentially shuffle them, reserialize them, and write back to disk. What you really want is kind of a file copy, which is a lot faster. So this is kind of processing all the data. And what's actually worse is you lose all the metadata too. So all those metadata files that I showed before, they all had a point. Like they all was keeping histories of the Iceberg table, like different snapshots, different schemas, things like that you probably don't want to lose. So if you do this, while the data looks good, all the history is gone. So you can try optimizing, and I think some people tried. One way you can also do this on your own is this was an attempt to do it. You can always find all the source files of the source table. So basically, you have to look for files in the current snapshot of Iceberg. Then you can use a file level copy tool like thiscp or some third-party tool that does kind of a quicker file copy. And then you create the target Iceberg table. And then Iceberg has already a procedure called add file, which generates a metadata file for a data file. So then you generate all the metadata, and then you can call register on the target catalog, which says, oh, this is now the target table. This sounds like it's good in practice, right? Like it's performance, but there's actually a lot of pitfalls for this. First, after they introduced delete files in V2, this whole thing kind of fell apart because now the delete files, you copy them over, but their references are broken. And so you actually have rows that become undeleted, which is quite dangerous. And actually worse is, you lose all the metadata, as I mentioned before. You lose all the history and stuff. But if you don't do the process of reading and writing the data back, you actually can't read a lot of the files that you just copied over blindly because maybe they need the old schema or old partitioning spec, and you don't have those anymore if you're just doing the file level copy of the data files. And similarly to the previous one, you just lose history in general. You cannot roll back to previous snapshots and things like that. So this is kind of closer, but not yet there. And then workaround 3, I think, was pushed by AWS in the community, was using MWrap. And MWrap is kind of like an AWS feature that you can have a kind of a global access point where you kind of say all the objects are MWrap paths, all the Iceberg references are MWrap paths, and this kind of works like a relative path thing because behind the scenes, AWS can kind of like switch from a primary to a secondary bucket. So this is kind of like more optimal, like having relative paths in Iceberg. It's kind of workaround for the fact that Iceberg doesn't have relative paths, but it's really limiting too. Obviously, it only supports AWS. The failover is requiring you to configure it. And I think worse was actually like AWS has no knowledge of the Iceberg file layout, so it just copies when it feels like it. And then so when you query the Iceberg table on the target side, you have sometimes incomplete data, which is really terrible. And again, this is only for, or not again, like this is only for disaster recovery case. If you ever, if you can't use this just to copy a table to your friend, for instance, right? This is more like heavy duty BDR. So then that's why we decided in Apple to build a table replication workflow. And what kind of, I think there's different, I think Netflix also had one, but in Apple, what kind of worked for us was this 3-step process. So we know metadata is gonna be broken. So we kind of first rewrite all the metadata of Iceberg, everything that's gonna be broken, and we fix that. We put it in a staging place. Then we essentially copy all those stage metadata and the original data to the target. And then on the target side, we check if everything looks good. And if everything looks good, we call register that metadata file to the target catalog. If you know the catalog API, there's a register table where you can kind of make a table from a metadata file. So this is the 3-part process that we use in Apple to do kind of like Iceberg replication. And we were able to contribute to the community in version 1.8 with this new action called rewrite table paths, which is a Spark action. You may know Iceberg has a lot of Spark procedures like rewrite data files, rewrite manifest. So this is another one. And essentially, it's the first part of the workflow, basically rewriting all the metadata files so that all the references are fixed. And then, yeah, as I said, it kind of, well, the arguments, you take the source location, like a source bucket directory, and a target location, like a target bucket directory, and then a staging location. And what it does is it kind of replaces all the /source to /target and all the metadata, puts it in the staging area, and then it's kind of like serves as an input to the thiscp or kind of like the copy tool. Basically, it returns you back both the metadata that I just rewrote, as well as the data files that those reference, so that now the thiscp can just take that and copy it over. And another thing it returns is the name of the kind of the root metadata version, the last metadata version file it copied, so that you can, on the target side, just take that and register it with the target catalog, and everything works pretty well. To give kind of an example of how this works, or how it looks like on disk after this operation. This is like an example Iceberg table. So you already see kind of how messy this thing is. If just by 2 snapshots, I couldn't fit any more in this slide, but like just 2 snapshots, you already have a ton of references that you need to fix, right? Each metadata layer points to the bottom one, and then by having 2 snapshots, you actually have a ton of back pointers as well, because if you're adding a file, you need to refer back to the original files. You're adding a snapshot, or you need to refer back to the original snapshot so you can roll back, and it just keeps going on. And so when you run this operation, the first step is so you run it with saying, I want to replace /source with /target. I want to move this to /target. It goes ahead and puts everything in staging, and it replaces all the paths. So the previous one was /source. It replaces it with /target. Notice that we don't do anything with the data files. We don't have to rewrite them because we want to be more performant. So we just pretty much rewrite all the metadata and then leave the data files. But then we return all the paths to distcp, and then distcp can take that one, copy it over, and then everything actually works pretty well because now you already rewrote all the metadata. So when you rewrite it on the source side, those kind of like they're not really that meaningful, but once you copy it over, everything snaps back into place. And then because everything is now the right path. And then you can just do register table. In this case, target metadata 2 was kind of the root of the table in the source, so we returned that one. And then you can use that to register to the target catalog. So actually, I think that's pretty much all I had. And then like Hongyue can keep going about like different problems that we try to solve.
Can I get this? Sure. Thank you so much, Xihang. So let me expand on the second part of this. So one of the problems we had for the replication or the disaster recovery is that we need to do this often and frequent. We're living in a world where there's a lot of data change. If we only need to replicate them once, that would be ideal, but that's not the case. So take some example. Think about the streaming Iceberg table we had. Oftentimes, we have a single table getting its data from a Kafka topic, and data being constantly appended to the tables every hour, or even minutely, because some of the data sets has a high data refreshment requirement. We need the data to be real-time or at least near the real times. So there's a lot of change on the source table, and we need to periodically apply such change to the target table. So how do we handle the incremental will be the problem. Let me start with a really simple example. Let's say I just create my own tables. This is called db.source, and I'm writing a single row into the tables. As Xihang mentioned earlier, the Iceberg maintains its hierarchical metadata structures. So for writing a single row, we'll end up have 4 different files. The top 3 files are the metadatas, and the bottom one is the Apache data files. When we try to replicate them for the first time, we will create a new target table. And we will expect the same data and same snapshot history as the source table. So when we're trying to read, we see there are single rows, and we saw on the target tables, we have 4 files. They're basically identical. The only thing different is their path. So the source table starts from the source, target table from target. So that's good, that's easy. How about I continue writing to my source tables? So for the second write, I'm just trying to provide a very simple example. I'm also inserting, but this can be either updating or deleting. From the Iceberg perspective, it's the same. All the data change will generate new snapshots. So on the right-hand side, we can see that the latest metadata is version 2. We have a new snapshot. Snapshot 1 corresponding to the first row we inserted. The snapshot 2 is the second row we inserted. There's a few ways we can replicating this. So start with the most straightforward one. Let's say if we want to replicate this, we can look at what's the current version of the source table, metadata v2. So let's see what are the files necessary in order to answer the query of the table. So apparently, we actually need all 8 data files. because each row will need 4 files to handle. So if we do the dumb way, we need to replicate all 8 files. But we know that we already have some files on the target side. How can we leverage that? We notice that the data change are being encapsulated into the Iceberg snapshots. What if we can just copy them by the snapshot? Does that save us some time on the replication side? So over here, the way how we do the incremental replication is we specify both start version and end version. Those 2 versions does not necessarily to be adjacent. It can be a range from 1 to 100. Over here, because we only have 2 writes, so the start will be the first metadata, and the end version will be the second metadatas. And between those 2 metadatas, we can see what's changing in terms of snapshots. And each snapshot will resolve to the files, the manifests and the data files. So that by identifying the difference in terms of the snapshots, we have the ability to do this incrementally. So once we identify such snapshots and list of files to copy, we basically repeat the same process. As Sihan mentioned, for the metadata files, we rewrite them, put into a staging location. For the data files, we copy them directly from the source to the target. So if we done everything correctly, in the end, we only need to copy 4 files, which is second snapshots. And then in the target tables, we will have the same data as our source tables. They're in sync. Their history and the snapshots are also in synchronized. So that's the part about the incremental replications. And one might be curious, how does that work with other Iceberg features? Iceberg has a lot of concept around the branch, like you can write more branch similar to the version control softwares. And how do we handle with snapshot expirations? So let's dive into the snapshots. Earlier I mentioned Iceberg snapshot has this a beautiful feature called immutabilities. Every data change will create a new snapshot. And if you apply the row level operation like inserting, updating, deleting rows, will also generate a new snapshot. We always move forward, so we never go back and modify the existing snapshot. That's why for the replication, we can just look at what's the difference in terms of snapshot and put them onto the target side. But something to notice here is that snapshot itself has some overhead. Like it helps with time travels. We can go back to a point in time and look at the state of tables, but we cannot keep accumulating snapshots forever. We need to keep the metadata and data size in check. The snapshot expiration is one of the maintenance procedure in the Iceberg where they can unlink the reference and also delete those files are no longer used. So over here, the example on the right-hand side is we have empty table, we insert twice, so we have 2 snapshots. On the latest V3 of the tables, we expired the first snapshots. So as part of the snapshot expiration, we also removed the S1. So all the files associated with the first snapshots. And this can be a problem for the table replications. The first problem is that what if when we try to rewrite the metadata, the files are already being deleted? So this will incur some runtime exception when we try to rewrite the metadata files. The second part is that what if the rewrite succeed, but when we try to copy them over using DCPs, the files are already being deleted? Then this is much harder to catch because at the DCP stage, we expect all the file to be there. And this file not found will require a little bit more deep dive to understand what's the external process are removing the files. So based on our experience, I think we need to schedule them differently. And also, we need to apply the referential integrity check. That means when we're trying to replicate them over, before we register into the target catalog, we need to examine that all the files we copy are actually present on the file systems. There can be some runtime corruptions or user errors where we delete files are not intended. Now, let's look into the branch and the tags. And Iceberg support the branching as a way to do the data experimentations. Tagging are used as a way for the data auditings. When we think about branching, we think now we have a non-linear history about the snapshots. So another example over here, we have our tables. We write some snapshot S1, and we append additional data S2. Over here, we can create another branch which generates snapshot S3. But S3, it's special here. It's not the latest snapshot. So for user, when they're trying to read the table, they will not get to the S3 unless they specifically ask for this branch. But from the replication perspective, it's the same, because in the version 4 metadata of the tables, we still have all the snapshots. It's just that for the read of table, we go to S2 instead of S3. So when we're trying to replicate them, we take all 3 snapshots into considerations, and the branch will be taken care of. And similarly, sometimes when we do the data experimentations, we'll run into the problems. We want to roll back or reset to a previous version. So Iceberg supports this through the stop procedures. Like you can call Iceberg to roll back to a specific timestamp or older snapshots. Over here, we also have very similar tables. We have snapshot S1 on the first write and S2 on the second write. Then we realize, hey, there's something wrong with my data. I don't want S2 anymore, so let's roll back to S1. And that's the beauty of Iceberg. Allow you to move the pointer only without doing any destructive operations. So S2 is still being tracked and can be replicated to the target side, but the other future read will only look at S1. That's what's intended to have the source table and target table being disaster recovered. So I guess I'm trying to repeat myself. As long as there's no destructive operation or anything resolved to the link reference of the Iceberg tables, existing replication workflow will take care of them for both branching and the rollback. So the next problems. We touched a little bit about the concurrent modifications. I want to clarify this. The modification to the Iceberg table can be categorized in a few ways. The first is the row-level operations. When you insert, update, delete rows into tables, those are being taken care of because they're all generating a new snapshots. As long as it's snapshot-based modifications, we're able to handle them pretty well. But there's always something else, like the file level of modification where some files gets deleted or removed from the disk without knowing by the Iceberg. So the problem with this is, as we mentioned, expired snapshot. That's where we are removing the files from the disk, and we want to avoid running this together or concurrently with the rewrite table path and the CP. So what we find out that it's probably better to run the snapshot expiration before the replication workflows. That gives us 2 benefits. First, it will avoid any runtime surprise where the files are supposed to be rewritten or copied will always be there. The second part is that if we expire snapshot ahead of time, that actually reduce number of files we need to copy it over. So that also save on the I/O. Other than that, I think concurrency is not giving us any more surprise. So with both incremental replications and ability to handle with concurrent modifications, the problem we see last is about performance. We all know that once we have these disaster recovery solutions ready, we want to apply to a lot of our production tables because those are the important ones. But usually those are the tables with much larger in size, and sometimes these can cause cluster resource problems. One of the common example is we had one production tables. It has tens of thousands of snapshots. They have been building data sets for years, and it's very hard to apply any regular maintenance to the table. But we still want to have the DR on top of those tables because the data loss will be the last thing they want to see. So so we have to make some trade-off here. Either we want to preserve the entire history like any other tables, or we just want to have the minimal available into the target tables so that we can build on top of this in future. And let's say, look at the example below. Let's say we have 103 snapshots. Instead of replicating entire tables one by ones, let's just look at the latest snapshot 103. If we can just replicating this, all the future read on the target side will still work, but it loses the ability to go time travel. The way how we do this is very similar to the incremental replications. We examine the snapshots, but instead of finding the difference between the start and end versions, we just pick the latest snapshots and replicating them over. One thing to notice that is this kind of filter need to apply consistently. So the source table can change. We can have snapshot 104, 200, 1000. And when we're replicating them, we want to make sure we're forward-looking. We're not trying to replicating the S1, S2, which doesn't never exist in the target tables. So when we leverage a technique like this, we can speed up our replications for the large production tables, but those are the selectively enabled for the tables where we cannot. The vast majority of tables, they still need to go through all of the snapshots. So we have the exact or identical copy between the source and the target. So the current state, as Sihan mentioned, in the Iceberg 1.8, we have contributed the first out of 3 steps into the Iceberg open source. We have the ability to rewrite the table metadata. It's being used into Spark actions and also Spark stored procedures. There's a second and third step where we're still continue to working on. One of the part we want to highlight is we need the referential integrity check to make sure all the file links are still there and that they're consistent before we register them. We don't want to see the problem when we query the target tables. Showed up some of the files are not found on systems. And also, when we're trying to register them, especially for the incremental copies, we want to make sure we have the ability to do it atomically so that either all of the registers succeed or not at all. We don't want to stuck in the middle state. Once we have this in the Iceberg 1.8, we actually get a lot of feedback from the community. There are surprising way of using these features. We have one of the team from China, they're using this to do the online Hive to Iceberg migrations. They can help solve this problem because they do not incur any downtimes and require 0 user actions to migrate 5,000 of Hive tables to the Iceberg. There are some bugs being reported from the community where some of the manifest we have rewritten has a different size. So it's not a problem for the Spark, but some engine like Trino, they rely on the Iceberg metadata to provide accurate sizing. And that's something we're looking to solve. And lastly, I think the best way to solve this problem is probably using a relative path, very similar to Delta did, where the path in the metadata is based on the table location instead of the absolute path everywhere. So that will increase the portability of the Iceberg tables. However, we need to think twice about the location ownership. What if someone is not authorized, they're trying to copy your tables by replicating them to their own location? So we're looking forward to that in the Iceberg v4. I think that's all we have. Yeah. We're ready for any questions.
Yeah. Thank you.